Hello class. I hope your preparation for the upcoming final is going well. I decided to create a video for the last class so you have this as a reference as you prepare for the final. This semester we covered two major types of statistics. Descriptive, which are used to organize and summarize data, and inferential, which are used to answer questions through analyses and interpretation. The majority of the semester we focused on this second type, inferential statistics, and so that's what I'm going to spend most of this PowerPoint talking about. So within inferential statistics, we have two major groups that we've really talked about. One is comparative, which is used to compare groups to see if there's a difference between them. In particular, we've looked at comparing groups to see if there's a difference between their means. So we would compare a sample with a population, for instance, to see if there's a difference in the means between those. Additionally, we've looked at associative statistics, which are used to assess the association between two or more variables. So we have an X variable, we have a Y variable, and we're looking to see if there's some kind of similarity in the pattern of scores between those two. With comparative, we really talked about 5 major tests. We talked about a one-sample z-test. This is used to compare a group to the population when the population variance or the standard deviation is known. We also talked about a one-sample t-test. This also is used to compare a group to the population. However, in this case, the population variance or standard deviation is not known. We also looked at an independent samples t-test. This test is used to compare two unrelated groups. So for instance, a quasi-experimental design might use an independent samples t-test if we're looking to compare males and females on some type of variable such as aggression or intelligence or emotional intelligence. And so if we want to look and see if there's a difference between males and females on one of those variables, we could use an independent samples t-test to make that contrast because we have two groups and we haven't matched them on anything prior to the beginning of this experiment. Now, if we were looking at the dependent samples t-test, here we're comparing two related groups, but we've matched them. So maybe we're using a pre-post design where we have the same person and we're looking at before and after our intervention. Or maybe we've matched the individuals. So let's say that we're looking at the impact of some sort of training on statistical ability, and we want to see, well, maybe originally, the math ability is influencing the efficacy of this statistical intervention, and so we want to match the individuals on, SAT quantitative scores prior to starting our study and make sure that we have the two highest people, one person in the intervention group, one person in the control group. And then when we look at the next pair, we want one person in the intervention group, one person in the control group. So we've matched individuals on some variable of interest prior to the beginning of the study. And as a result, we're really focused on the difference between those two individuals as opposed to just the group means. Additionally, we can look at one-way analysis of variance. And here, the distinguishing factor, and it really is quite easy to identify when we're looking at it, is that we're going to see 3 or more groups involved in the experiment or in the comparisons that we're making. As I mentioned, in addition to the comparative inferential statistics, we also looked at associative inferential statistics, which is when we're looking at the connection or the correlation between 2 or more variables. So one test that we looked at was the chi-square. This is used to evaluate the association between two nominal variables. So a little shout out to Ross, right? Nominal variables, we're rocking those with the chi-square, right? Because we're looking at the relationship between, let's say that we're looking at the relationship between socioeconomic status measured as low, moderate, and high, and likelihood for drug use measured as low and high. If I want to look at the association between those two variables, now admittedly we could make an argument that they're kind of ordinal in nature. We could look at different types of ways of evaluating these ordinal types of scales, But on some level, we really have a differentiation, right? We have 3 categories of socioeconomic status, and we have 2 categories for drug use, whether it's low or high. And we can then look at the association between these 2 nominal variables by using a chi-square test. Additionally, when we're looking at these associations between variables, we can use a bivariate correlation. Now, this is used to evaluate the association between 2 continuous variables or a continuous variable and a dichotomous variable. So going back to that example where we have socioeconomic status and high and low drug use, if we look at socioeconomic status as, income in dollars, now we've really shifted our unit of measure from more of a kind of categorical or ordinal variable into a continuous variable. And with that continuous variable in dollars of income per year, we could use a bivariate correlation, and we can still use that with the dichotomous variable of high and low drug use, or we could look at drug use as maybe frequency of use per year, or likelihood of use within a week, something like that, which again we're then shifting from a dichotomous scale to a more continuous scale, and a bivariate correlation would still allow us to evaluate that data. A bivariate regression in regards to simply the data that we're using is very similar to a bivariate correlation. We're still using 2 continuous variables or a continuous variable and a dichotomous variable. The difference here is that we really are often implying directionality. So if I think that having more money available provides more resources, and as a result of that, then maybe you have different coping strategies, or maybe you're making use of prescription medications instead of using what we would typically refer to as drugs, right? Even though they are themselves a form of drugs. There's a directionality that's kind of implied by that. And so if I'm applying a directionality, then it may be appropriate at that point to use a bivariate regression. We also talked about some of the assumptions that are connected with these types of statistics. So in particular, we talked about random sampling, independence, normality, homogeneity of variance, homoscedasticity, linearity, and causality. With random sampling, the sample is randomly drawn from the target population. So by this, if we were focused on West Texas A&M University and the 9,000 plus students at West Texas A&M University, if I wanted to draw a random sample, I would need all of the individuals from West Texas A&M University within a data set or a pool of individuals. And what I can then do is, from that pool of individuals, randomly draw 100 or 1,000 in order to represent the whole. And through that random sampling procedure, what I can do is I can get a good sense that my sample should generalize to that larger target population. Additionally, we often need independence. And by this, what we're talking about is that the cases within each sample need to not influence each other. So, for instance, we might want to collect our data individually or independently, so that with this, I don't have a group of individuals doing the test all together and having within that group, having the individuals possibly influence each other's scores. We also look at univariate normality. With univariate normality, we're looking at one variable, right? Univariate, one variable. And here what we see is an example of what univariate normality might look like for an IQ score. So we have a mean of 100, we have standard deviation of 15, and the most frequently occurring score is at 100, right? So the most likely score of all of our possible scores is right at the mean. And then what we see is that as we go above the mean and below the mean, at equal distances above and below the mean, we also have an equal level of frequency, but a frequency that is less than the frequency right at the mean. So the frequency of 115 and the frequency of 85, both of which are 15 points or 1 standard deviation from our mean, the frequency of those scores is equal to each other, and it is less than the frequency of scores that we see right at the mean of 100. Additionally, as we go one more standard deviation out to 70 and 130, what we see is the frequency of the scores at 70 and 130 is approximately equal, and that frequency of scores is less than the frequency of scores at 1 standard deviation above and below the mean. So as we move away from the mean, we see the frequency of scores going down, and we see the frequency of scores going down at a similar rate when we go above the mean and when we go below the mean. Now, when we are looking at bivariate normality, this is where we're looking at an x variable and a y variable simultaneously. What we are talking about with bivariate normality is that the distribution of y scores are normally distributed at each level of x, and the distribution of x scores is normal at each level of y. So what do I mean by that? What I mean is, let's say that we go in where x equals 0. Let's say that I just look at that narrow range of scores. So I look at all individuals who have an x score of 0, and I look at what does their y scores look like. What I should see is this normal distribution of scores when I pull their x scores and I look at their y scores. Conversely, when I pull a score on y, what I should see is that at that level on y, all of the x scores are normally distributed. So if I'm looking at y, 1 standard deviation above the mean, what I should see is that at that score, there is a mean for x, and that around that mean of x, the scores for x are normally distributed at that level of y. And I should see that for all y possible scores and all possible scores on x. I should also see that with y being normally distributed at each of those levels on x. Equal variances, or homogeneity of variance. What we're talking about here is that the degree of variability in the populations is relatively equal. So in particular, this is important for things like independent samples t-test and the ANOVA, because what we need to see is if I'm comparing men and women, for instance, let's say that men are the group on the left here, that's their distribution of scores on a variable. Women are the group on the right, and that's their distribution of scores. And so let's say we're talking about emotional intelligence. Well, if I'm wanting to say that men and women are different on that emotional intelligence, first and foremost what I need to do if I'm going to use an independent samples t-test is I need to make sure that the variance for that emotional intelligence for men is roughly equal to the variance on emotional intelligence that I see in women. And if that's the case, as is presented in this diagram, then we can kind of move forward with the independent samples t-test. Now, if I see a situation more like the one here at the bottom of the screen, where the men have one type of distribution and the women have another type of distribution, now we've possibly violated that equality of variance or that homogeneity of variance assumption, and I'm going to have to use a different type of test. In this particular case, I would probably use a Welch's test in order to address the violation of that assumption. Homoscedasticity. And the idea here is the scores on y should have roughly equal variance across all levels of x, and x should have roughly equal variance across all levels of y. This is particularly important when we're looking at things like correlations and bivariate regressions. So here I have a scatter plot like one would see if we were looking at a correlation or a bivariate regression where we have x and we have a y, and we're looking at the scatter of scores around the fit line. And what we see is that in this case, where we do in fact kind of meet that assumption of homoscedasticity, the variability of scores around that fit line is roughly equal throughout the entire range of our scores on X and throughout the entire range of our scores on Y. Now, in contrast, this second example here, we see heteroscedasticity. What we see is that on the lower end of the range for X values and Y values, we see a fairly tight group of scores. So the variability within those scores is somewhat limited. It's smaller. Compared to when we look at the higher scores on X and the higher scores on Y, we see a broader range of possible scores in that area. We see more variability around that fit line. And so in this case, we would be concerned that we have violated that assumption of homoscedasticity and that we may not be able to do a correlation or a bivariate regression. One of the other assumptions of correlations and bivariate regressions in particular is linearity. And what we're talking about here is we are often trying to represent the association between X and Y with a linear equation. And if the association between X and Y is in fact curvilinear, it's not linear, then our ability to represent that with a linear equation, we can't really do that effectively. And so what we see here is that the example on the far right shows a curvilinear relationship between X and Y, where the relationship changes as we go across the range of possible scores on X, or looking at it differently, the relationship changes as we go across the possible scores on Y. And so in this type of case, we're not going to be able to effectively represent the association between X and Y with a correlation or a bivariate regression. The last assumption that we're going to talk about is causality. And really this isn't so much an assumption of bivariate regression in the math or statistical sense, but in more of the conceptual sense. When we talk about the interpretation of the bivariate regression, we often talk about it as a predictor and then the variable that we are predicting. And so because of that, we often are implying that one variable is the independent variable, or one variable is the cause, while the second variable is the outcome or the dependent variable. And because that's how we often talk about the interpretation or the meaning of the results from that bivariate regression, we often need to have a strong theoretical reason for X to cause Y. And we also need to, again, meet some of those conditions for causality, like temporal precedence. So here you see a nice kind of quick, easy reference for what types of assumptions should we be considering based on the test that we're conducting. And you can see the first 5 tests are those comparative inferential statistics. One sample Z, one sample T, independent samples T, dependent samples T, and the analysis of variance, or the ANOVA. Then the next 3 tests are the ones that are the associative inferential statistics, with chi-square correlation, in this particular case bivariate correlation, and bivariate regression. And so we can see the assumptions that we should be meeting in each of these cases. And we've already talked about those to some degree, but you can kind of quickly go down the list and, for instance, independent samples T. Well, we've added on that assumption of the homogeneity of variance, which again makes sense because independent samples T, we have 2 groups that we're comparing, and we need the variability on whatever variable we're comparing them on to be roughly equal between the 2 groups that we're comparing. Same thing for the ANOVA. We have that homogeneity of variance on there because we have 3+ groups. We're comparing them on whatever our outcome variable is, or whatever our continuous variable is. And so we need to see that the variance between those groups is roughly equal on that continuous variable. So really this slide doesn't have any particularly new information. What it is, it's a new visualization of the information that we've presented in regards to the two major types of statistics that we've covered this semester, inferential and descriptive. And within descriptive, we really talked about these relatively early in the semester, and then we made use of them to some degree throughout later statistics. But what we're talking about there are things that we can use to organize and summarize the data, such as the mean, the median, the mode, frequency of different types of scores within our range of possible scores. Now, what we spent, again, the majority of the time talking about are the inferential statistics. And within that, we had those two major groups, comparative and associative. Again, with comparative, we had the 5 major tests that we talked about: one sample Z, one sample T, independent samples T, dependent samples T, and the ANOVA. And with the associative, we had the 3, the chi-square, bivariate correlation, and bivariate regression. Now, to add a little bit of information about those inferential statistics, when we're looking at the comparative statistics, we're really looking at different comparisons. So in particular, one sample Z, we are comparing the population to the sample, and in that case, the standard deviation or the variance for the population is known. In contrast, one sample T, we're also comparing a population to a sample. However, the standard deviation or variance for the population is not known. We also have independent samples T. In this case, we're comparing a sample to a sample, or maybe a group to a group, and there's no use of matching or pairing or repeated measures. With the dependent samples, it's distinct from the independent samples because while we are comparing a sample to a sample or one group to another group, we are using matching or pairing or repeated measures. So again, we may have a pre-post design where we have the same person before or after an intervention, or we may have a matched pairs design where 2 individuals have been matched on some variable of interest prior to the start of the study, and then we assign individuals from each of those pairs to our 2 conditions. So one individual from a pair goes to one condition, and the other individual from a pair goes to the other condition. Finally, with the ANOVA, again, it's one of the easier ones to pick up on because we're really comparing 3 or more groups in this case. And so it kind of tends to stand out just because of the sheer number of groups that are involved. All right, with the associative inferential statistics, we are going to associate, in the case of the chi-square, a nominal variable with another nominal variable. So again, here we have a categorical type of variable such as male-female, and then we are looking at the associations between that and another categorical type of variable such as college major. Maybe I think more females still tend to go into the education department, for instance. And so we could look to see, is that the case? Is there an association between the gender and college majors where males maybe still tend to be more dominant in engineering or something like that, which has been stereotypically dominated by, or historically dominated by, men. But as over the course of time, we have seen a reduction in the differences between those, but we want to see, does that historical difference continue? And we could look at more current data with college major being one variable, again categorical, and gender being another variable, again categorical, and we're looking at the association between those 2 nominal or categorical variables. Now again, with bivariate correlation, we're looking at a continuous variable with another continuous variable, or a continuous variable with a dichotomous variable. And kind of leading up to the bivariate regression, here we haven't assumed any particular directionality. We just think that there's an association or a link between these 2 variables. And with bivariate regression, we have a continuous with a continuous, or a continuous with a dichotomous. However, directionality is implied, often because of the way we interpret the statistics and talk about the results. But we often imply that by the way we talk about it. And so we often want to meet those assumptions of causality so that we can feel confident that we are doing it in a context where it makes sense to do it.